All right, so we are starting the last activity in Unit 5, and I saved this one for the end because it's a little involved as far as the setup. And we're going to spend the next 3 days determining either density or volume of an object in multiple methods, so either by formula or by other means. So this will be a presentation on determining density to start. Density is defined as the measurement, the amount of matter per unit of volume, and then the more matter you have, the higher the density as compared to lower density. Any object that's more dense than water would sink in water as compared to any object that's less dense than water, which is going to float. When we do these types of calculations, we have to talk about whether or not we're going to be using mass or we're going to be using the weight for our calculations, and then discuss again the differences between the two because they're not the same. Mass is going to be the amount of matter in an object or quantity of the inertia of that object, as compared to weight, which is the force of gravity on mass. So I can determine the weight if I know the mass and I know the constant that we're going to use for gravity. Here's our formula then. Weight is mass times gravity. In the SI system, our gravity is going to be 9.8 meters per second squared. If we were doing US customary, it would be 32.2 feet per second squared. So mass and weight are often confused. As an example, a man has a mass of 100 grams. To determine his weight, you would have to take the 100 kilograms and multiply by our gravity, again 9.8 meters per second squared, and I determined that his weight in the SI system is 980 newtons. In the US customary system, if a woman weighs 100 pounds, we can determine her mass by using the same formula. Weight is mass times gravity. We're solving for mass in this case. I'm going to take the weight, which is 100 pounds, divide by gravity. And again, in the US customary system, gravity's constant will be 32.2 feet per second squared, so her mass is 3.1 slugs. So in the activity that we do, whether we're starting with mass or weight will determine which formulas we use for density. Okay? A lot of this information on this slide, it comes directly from a formula sheet. It's the conversion factor between kilograms and pounds, between slugs and pounds, so on and so forth. And so this information is not stuff that you need to memorize. It's something that we would be able to refer to view our conversions. When we're talking about mass and weight too, we want to talk about what pound force is as a unit of force. And it's going to be the gravitational force exerted on a mass, 1 pound on the same surface of the Earth. Again, these are conversion factors that we use. How do I get from pounds to newtons, newtons to pounds? Okay. Again, this is going to be on a formula sheet. You're not going to be expected to memorize these types of conversions. Finally, how are pound mass and pound force related? It kind of depends on the gravity. Okay. On the Earth, we're using a gravity in the US customary of 32.174. 1 pound mass object weighs 1 pound force. So they're equal. If we're talking about in outer space and there's no gravity, then 1 pound mass object has no weight. And on the moon, if the gravity is 5.32, then 1 pound mass object weighs 0.166 pounds of force. So again, it's going to be based on gravity that determines this type of number. All right, so let's talk about density then. Density can be indicated in multiple ways. It can be mass density, so if I know the mass for the object, I can do the mass per unit volume, or weight density if I know the weight. So if I've taken the mass and I've already multiplied by our gravity, I can do the same type of calculations based on the weight of the object. Okay. So either way, we're going to know 2 of the variables and we'll be solving for the missing variable. So if I'm given mass and I'm giving volume, I can determine density. If I'm giving volume, I'm giving density, then I can figure out what the weight for that object would be. The types of units that we would use depending on the system. So in the SI, it's going to be grams per centimeter cubed or kilograms per meter cubed, and in the US customary, pounds per inch cubed or pounds per feet cubed. So if I look at this as an example, give me some common items and what their density would be either in mass density or weight density. Again, we talked about anything that is lighter density-wise than water is going to float. So if I have a density of 0.64 for an apple, we'd expect that apple to float in water. Same with ice. But these others, which have a greater density, are going to sink in the water. All right, so let's talk about the instruments then we're going to use in these types of calculations. If I'm using a balance, and you may have used this before, like when I go to the doctor, I stand on a balance and they move the little weights across. This is used to record mass. Objects known to find mass, okay? And the reason that it's mass specifically is that they are unaffected by gravity. In fact, the gravity doesn't affect the measure that's being recorded by a balance. For the activity that we're doing today, we're going to use a scale. And the scale does take into account the force caused by gravity. However, most scales can, especially ours that are digital, also convert it back to what the mass would be. So it would have the constant of gravity factored in and can determine the mass for you as well. So finally, if we're going to be doing these types of calculations with density, we're going to need to also be able to calculate the volume for the objects that we're using. It's going to be the amount of three-dimensional space enclosed by the object. And we have two methods that we can do these types of calculations. The first one we've already done before is to calculate using the geometry of the shape, meaning there's a formula I can use to determine the volume for that object. The other method is going to be the indirect method, and we're going to use water displacement to determine the volume. This would be for circumstances where we don't know a formula that we can use to determine the volume for that object because it's an irregular shape. So if it's simple and geometric, like a sphere or like a cube, there's a formula I can use, right? I can take a caliper, I can measure the sphere, determine what the radius would be, plug that in, and determine the volume. Same with the rectangular prism. I measure the height, width, and depth for that object, multiply those, and then I get the volume for that object, okay? If it's an irregular object and there is no formula that can be used, like let's say the people in the Automobile's car, I don't have a formula. I'm going to use water displacement to determine the amount of volume in these objects here. To do that, I first place water at a certain level in a graduated cylinder. So I need to record where the starting level is. Make sure that you're recording the meniscus. That's where I'm going to read this at the bottom of the curve here. I'm going to add my samples, whether those are stones, Automobile's people, and when I do, the water level is going to go up. When I record the new level, after the samples have been added, the difference between the new level and the original level is the volume for those parts. So for those types of objects, that's how we're going to determine the volume, the difference in the sample volume. Let's do an example then before we talk about today's activity. Given the density of what is the density of a 2.24 inch diameter sphere of titanium, so you know the material that weighs 0.82. So given the diameter and knowing that it's a sphere, I know I can use a formula to determine the volume, and I know how much it weighs. So I'm going to be doing volume. 2.24 is my diameter, divided by 2 to give me the radius, cubed, and I get 5.88 inches cubed. If I'm going to be solving for the density of the object, I know the weight and I know the volume. I plug those numbers in, I get a density of 0.14 pounds per inch cubed, meaning that the density for this material, titanium, is 0.14 pounds per inch cubed. Given that, what volume of water would be displaced? I can plug my numbers in and determine that if I were to do water displacement, it would be 96 milliliters of water that would be displaced. So let's look at today's actual activity. We're starting 5.3. This is going to be broken out into multiple days. Part 1 will start today. Part 2 we will start probably tomorrow. This will be a group assignment, meaning that the group will be responsible for turning in one document, and all members of the group will receive credit for that document. So the supplies that we'll have will be a scale, ours will be a digital scale. We'll have the graduated cylinder starting tomorrow, a caliper for recording measurements, the Automobile's people and wheels. And the samples we're using today are the wooden puzzle cube, the steel sphere, and the Delrin sphere. Delrin's like a plastic. Given those materials, we're going to work through part 1. And part 1 is basically populating this chart of information to determine the volume, the density of these samples. So you choose between whether I'm going to use the mass or the weight. I would recommend mass because the scales we're going to use are going to give us our answers in grams, which is the SI system. Okay. And we're going to go through the process of determining the mass of 10 samples. So if there's 10 Delrin balls or plastic balls, I can determine the mass on my scale, record that number here. When it asks for an average of those, that would be basically this same number divided by 10. So what an average mass would be for the object. Do the same thing for the steel and the wood. Second part then, what formula would I use for a sphere or for a rectangular prism to determine the volume? I'm just adding the formula here. Then using 3 separate samples, like one measurement, the diameter of one Delrin ball, the diameter of one steel of one of the wooden cubes, and do that 3 times to get the volume. Okay, we're going to show the work on here. And then finally, we're going to use the formula for density to determine the density of that material. Okay, so we're working through part 1 today. Part 2 is where we'll start the irregular shapes where we can't use the formulas to get volume, and that's when we'll do the water displacement. But it's the same idea. We work through determining the mass of these samples and so on and so forth. There are also conclusion questions at the end, and all of this you can work directly on the Word document. In fact, you may just have one member of the group do it on theirs, and then you can turn it in for the group to receive credit. A couple tips before we get started. When you're using the scales and you're taking mass measurements for the Delrin and the steel, the rounds, they're going to roll off, use the Petri dish as a way of containing them. But when you put the Petri dish on the scale, make sure that you zero it out. Don't include that as part of your mass measurement. It needs to be zeroed out. Okay. We want to try to get all of those measurements today. We'll do the same thing tomorrow because I have to give those scales back to the biology department. They don't belong to us. So we'll have 3 days to work on this. Group activity, 1 submission for the group, which will be due probably at the end of the week. We'll have 3 days of class to work on it, and then we'll submit the finished document at the end of the